Hello students, welcome back. The next topic is implicit differentiation. Let's go back to the same example that we studied in lesson 6. Here it is. Do you recall this? It's an implicit relation. Please note that x and y are related based upon an implicit equation. X to the third power plus y to the fifth power equals to 3 plus x squared times y cubed. And do recall the picture as well. It turns out this implicit relation gives rise to not just one curve, but two curves. As a matter of fact, it turned out I was wrong. There are three curves. Here, I drew from -1 to +3 only, but let's go a bit further, -5 to +5. You see, there are three curves. Previous picture was pictured only about this much. That's why I thought there were two curves. In fact, there are three. Anyway, that's a problem. And then we can take the derivative implicitly by x. What do you get? Well, that's what you're going to get. Take the derivative of x cubed. We get 3x squared. No problem there. Take the derivative of y to the fifth power. We have 5y to the fourth power, but y prime pops up. Whenever you take the derivative with respect to y, y prime pops up. The same goes to the right hand side. And if you want to remind yourself about the reason, well, it's coming from the chain rule. You have to consider y as a function of x, at least locally. So y of x to the fifth power, y of x to the third power. And then if you take the derivative, what happens? Power comes out as coefficient, subtract 1 from the power because the chain rule says the derivative of the outer function first. And then inside never changes. And finally, the derivative of the inside, y prime. So that's how we get y prime, by the chain rule. The same here. And then what did he do? So for y prime, and we can express y prime, the derivative, using x and y. Remember this? Also, please recall that some people use this German notation, dy over dx notation, in place of y prime. Some people even take point off for using y prime. I never do that because I prefer y prime over this. Our textbook author prefers dy over dx. Me, I prefer y prime. The reason is because it's 21st century. Y prime expression is associated to computer algebra system and symbolic programming, as you can see in this simple coding. Let me expand these. And please note that the first outcome is the same as this implicit differentiation we did manually. Yeah, they're the same. Some change of order, but that's it. You see, both the addition and multiplication are commutative, so it's okay. They're the same. And the second line corresponds to the answer here, y prime. And then here, in the outcome and also in the input, we use y of x and y prime of x. Not just Mathematica, but everywhere actually. In all computer algebra system, Mathematica, Maple, MATLAB, Magma, they all use y primes, not dy dx. Okay, so much for the review on implicit differentiation, and I did really thorough review, and I did it for a reason. Now let's go to our new topic, the implicit differentiation of parametric functions, but let's stick to the same relation. And then, of course, same curves. Now, let's consider both x and y are functions of t. T is typically time variable. Some people call it parameter, but I'd prefer to call it an independent variable. Now let's take the derivative with respect to t implicitly. In that case, what happens? x to the third power will become 3x squared, but by chain rule, x prime will pop up. And then 5y to the fourth power, and then y prime will pop up, and so on. Make sense? Let's color code this. X prime is blue and y prime is red. Same goes to the right hand side. That's because both are functions of t, and chain rule applies for both. Here's the outcome. Does everybody agree? Right hand side, we use the product rule. Derivative of the first function, so 2x, and then x prime popped up. Derivative of the second function, 3y squared, and then y prime popped up. Again, if you want to see the reasoning, you can consider both the x and y as functions, x of t to the third power, y of t to the fifth power, and so on, and then take the derivative. By chain rule, we have to take the derivative of the outer function first. 3 comes out, subtract 1 from the power, and then inside never changes. Finally, we multiply the derivative of the inside, x prime. It's a chain rule. Same here, y prime. It's a chain rule. Product rule, and then when you calculate the derivatives, chain rule, and then chain rule. That's why we are having x prime and y prime by chain rule. Now, we have original relation, and then by taking the implicit differentiation, we got the second relation. So we have two relations, consequently two equations. But there are 4 unknown variables out there. X of t, y of t, x prime of t, and y prime of t. They're all dependent variables. They're all functions of t. In any case, they're all unknown variables. But 4 unknown variables with only 2 equations, it's hopeless. You cannot solve it. But if the system somehow gives you 2 of them, and then we bring it down to a system of 2 equations and 2 unknown variables, sometimes we can do it. And that kind of problems are called related rates, you see. The original functions, x of t and y of t, are related by the original equation. On top of those, the instantaneous rate of change, x prime of t and y prime of t, those rates are related by the second equation. So rates are related rates. So these kind of problems are called related rates. Before going over to actual problem on related rates, let me show you one more picture. Some more computer algebra system stuff. One further comment. Some people use dx dt and dy dt notation in place of x prime and y prime, but me, I prefer x prime and y prime better. I know, some people hate these x prime, y prime, and some people even take point off. I know some of my colleagues do that. And our textbook author certainly prefer dx dt and dy dt, but me, I like x prime and y prime better because they are better suited for computer algebra system and mathematical programming. Here's the outcome. Please compare this with this computation we did. They're the same. So using x prime t, y prime t, you can actually program and then do these kind of things. So there's no reason to move away from x prime and y prime. Actually, there's every reason to move into x prime and y prime out of dx dt and dy dt. This 21st century. Okay, alright, so much for the digression. Let's come back to the visualization I told you about. Using computer algebra system, we can actually solve the system and then visualize like this. You see, previously, again using computer algebra system, you can graph this relation. We have 3 curves like this, but that's static. Now, if you use vector functions and then use the solutions based upon time variable t, then we can get dynamic solution like this. You see, you get moving dot model. 3 dots, because there are 3 solutions. blue, red, and green, each gives you x of t comma y of t, a vector function. So first solution vector function, blue, second red, third green. And why are there only 3? That has something to do with this relation as cubic power, x to the third power. So cubic equation, so 3 solutions. I don't want to get too deeply into that. So practically it is a little bit hard, but at least theoretically, any implicit relation of x of t and y of t can be considered as parametric function model or a vector function model. And once you get a vector function model through position vectors, then you actually get a dynamic solution. Here's one such visualization. Okay, all right. So much for the visualization and the motivational example. Let's go to an example problem on the related rates. This one is much simpler. Because we want to get to the bottom of it, we have to start from something simpler. X and y are both functions of t such that we have this relation, okay? X and y are related like this implicitly. And then if you take the derivative implicitly, then we are going to get a second equation, a relation between x prime and y prime. Now we have 4 equations, or excuse me, 4 unknown variables, xy and x prime, y prime. And only 2 equations is not good, but the problem gave you 2. X equals to 1 and y prime equals to -1. So these 2 are there, and you're looking for y value and x prime value. So only 2 unknown variables, y and x prime, with 2 equations. Yes, you can solve it. If you get those 2 equations right, of course. Here we go. Original, and then let's take the derivative implicitly and get the second equation. Go ahead and try. Is that what you got? X cubed became 3x squared, and then x prime pops up. The product rule, x prime y plus y prime, and then 3y squared and y prime pops up. Alright, we have 2 equations, number 1 and number 2. 4 variables, x, y, x prime, and y prime, but the problem gave you 2. So we can plug in these values, x equals 1 here, 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 and then y prime equals to -1. Well, okay, here we go. I plugged those in and we got these 2 equations. Can you solve this? Let's see. I think I can do that. I'll be simplified into this. And then 1 to the third power, so that's 1, and then just y, and then 1 cancel out. That's what you're going to get. That's the first equation. Second equation, this is 1, and then that's -1, and then that's -1, so negative. Okay, looks like we have these 2 equations. Can you solve it? This and that. I can solve the first equation because I can factor it and the right hand side is 0. You're going to get this. Make sense? Y times 1 plus y squared is equal to 0, and consequently y is equal to 0. You see, a times b is 0, then one of them has to be 0. But 1 plus y squared is never 0, it's strictly positive. So y has to be 0. Now, plug this into the other equation, and you're going to get the solution. The other equation becomes this, and then you get x prime equals 1/3. Please check. That's how you can solve a related rate problem. Original and the derivative, so 2 equations, and then plug in the numbers. So you have 2 equations and 2 unknown variables. Go ahead and solve it.